So here's what happens. So we've got our classical mechanics equations. We've got our quantum mechanics equations. Let's smash them all together. So we know we can write here that classically Jz is plus or minus PR. I'm just going to write that as PR, even though we know that's technically the cross product. Okay, and I know here the de Broglie wavelength that P equals H divided by lambda. So now that's a pretty obvious place that I can combine these. So I can say Jz equals plus or minus HR divided by lambda. Okay, and again, plus or minus because, right, I can be rotating in this orientation or I rotate in this orientation. Okay, so what is the wavelength for this thing? Well, the wavelength here is we're going to ascribe this closed loop or in phase motion. And to get that, what we're going to say is then the wavelength has to be some integer value of the radius. And that integer we're going to use, it's not an integer, rather it's a trigonometric function, 2 pi r, okay, to give us that 2 pi full loop. And then this is going to be divided by a new quantum number that will give us quantized in phase motion. So now we have no idea what letter to use yet, so we're going to foreshadow, and we're going to call the new quantum number M sub L, ML. That, in fact, is the ML that you know and love. That is called the magnetic quantum number, okay? And it can take on the following values. So for now, we're going to pretend that we don't know what values ML can actually take on. So when we try to figure out how we're going to do this closed loop motion, we recognize, well, it's got to be in these, integers of 2 pi or these circuits of 2 pi. So what that means is plus or minus 1 is okay. And again, the plus or minus for the, the change in angular momentum. It means that plus or minus 2 is okay as well. And as we shall see, we're going to be able to add other qualifiers to this ML. As it turns out, plus or minus 1 and plus or minus 2 aren't the only values that are acceptable. But for now, this is as much as we can say that is acceptable for this quantum number. Okay, so I think, let's see, I might have a picture of that coming up. But so now if we keep going with this and we recognize that Jz equals plus or minus HR over lambda, and then we substitute our quantized solution for lambda, then what we get is plus minus ML H times R divided by 2 pi times R. And all of that is going to equal plus or minus ML times H bar. So the radius and the radius cancels, and we know H divided by 2 pi is H bar. Okay? So what we see classically, let's see, I think I have that on the next slide. Yes. So we can see now that the energy associated with this particle rotating classically can be written as Jz squared divided by 2i. Okay? But as far as where quantum is concerned, right, we wrote that Jz is MLH bar. So that means when we substitute that MLH bar in for Jz, we get that in terms of quantum mechanics, E is ML squared, H bar squared divided by 2i, okay, where Jz equals MLH bar. Now, I only showed you that plus minus 1, plus minus 2 are what we think are acceptable so far. We're going to see later on, coming up shortly, that 0 is acceptable and that 3 is also acceptable, okay? We're going to see how that manifests. And what's also important to note that the plus minus, that means that these ML states are in fact doubly degenerate. So the ML plus 1 has the same energy as ml minus 1. They're opposite in sign, right? We recognize, you know, if it was 1, E then would be just h bar squared divided by 2i. But if it was a minus 1, it would be minus h bar squared divided by 2i. But those are degenerate because that negative sign, again, it just describes the different orientation, whether it's rotating this way or whether it's rotating this way. Okay? So now our next step is to determine if this is acceptable to the Schrodinger equation. Because we've kind of done this in sort of a backwards different way than some of our other problems. I mean, look, we already have a solution to the energy without even putting together a Schrodinger equation. We already have a quantized solution for energy. So we have to test if this is going to work for the Schrodinger equation.